Black holes are cosmic enigmas that twist the very fabric of space and time. But what if the biggest mysteries aren't the ones we see today, but the very first ones that ever existed? The universe's earliest black holes might hold clues to how everything began, and some of these theories are so strange, they'll make the known laws of physics seem tame. Were these ancient monsters born from the collapse of the first stars, or did they emerge from something even more bizarre, like cracks in the infant universe itself? Over the next few minutes, we're diving into 30 jaw-dropping ideas from black holes hiding extra dimensions to ones that could be portals to other realities. Buckle up, because we're about to explore the wildest frontiers of cosmic science. What if the very first black holes didn't form from dying stars at all, but were born in the chaotic aftermath of the Big Bang itself? This is the mind-bending theory of primordial black holes, cosmic relics that could have appeared when the universe was just a fraction of a second old. Picture the cosmos in its earliest moments, a seething, ultra-dense soup of matter and energy, riddled with violent density fluctuations. In some regions, matter may have been packed so tightly that it collapsed directly into black holes, bypassing the need for stars entirely. Stephen Hawking explored this idea, suggesting these ancient objects could range in size from smaller than an atom to massive enough to dwarf today's supermassive black holes. If they exist, primordial black holes might still be lurking in the darkness today, invisible yet shaping the cosmos in ways we're only beginning to understand. Some scientists even think they could be the elusive dark matter we've been searching for, ghosts from the birth of the universe hiding in plain sight. The hunt for primordial black holes isn't just theoretical. Scientists are actively searching for traces of them in the cosmos. One of the most compelling clues comes from microlensing, a phenomenon where the gravity of an invisible object bends and magnifies light from distant stars. If a primordial black hole drifts between us and a star, it could create a fleeting brightening detectable by telescopes. Projects like the Optical Gravitational Lensing Experiment, or OGLE, have scanned millions of stars hoping to catch these elusive flashes. While no definitive proof has emerged yet, even the absence of certain microlensing signals helps narrow down their possible sizes and numbers. Then there's the gravitational wave frontier. When black holes collide, they send ripples through space-time, and the echoes of these collisions could hold secrets about the universe's first black holes. Some mergers detected by LIGO and Virgo involve black holes with unusual masses, too light to be remnants of massive stars yet too heavy to fit neatly into current models. Could these be primordial black holes, ancient survivors crashing together billions of years after their birth? But perhaps the boldest idea is that these ghostly objects might solve one of astronomy's biggest puzzles: dark matter. If primordial black holes exist in vast numbers, their combined gravity could explain why galaxies rotate faster than expected without invoking unknown particles. It's a radical alternative to the search for WIMP or actions, one that turns the spotlight back on Einstein's gravity itself. Whether they're hiding in microlensing data, echoing in gravitational waves, or silently shaping the cosmos, primordial black holes could rewrite our understanding of the universe's earliest moments and its invisible scaffolding. Now, let's turn to one of the most exotic theories about the origins of black holes, one that doesn't involve stars, the Big Bang, or even conventional matter. Imagine the early universe threaded with unimaginably thin, ultra-dense filaments of energy, cosmic strings left over from the very first moments of creation. According to string theory, these bizarre structures could have formed as the universe cooled, stretching across space like cracks in frozen ice. And if these cosmic strings ever became unstable, twisting or intersecting, they might have snapped under their own immense tension, collapsing into black holes in an instant. The physics behind this process is as mind-bending as it gets. cosmic strings aren't made of matter as we know it. They're defects in space-time itself, so dense that just an inch-long snippet could weigh more than Earth. If one of these strings looped or knotted, its gravitational pull could become so intense that it crumpled into a singularity, birthing a black hole without a star ever existing. String theory even suggests these objects could have extra-dimensional properties, warping reality in ways we can barely calculate. But here's the catch: cosmic strings are purely hypothetical for now. No telescope has ever spotted one, and their ghostly nature makes them nearly impossible to detect directly. Some researchers look for their fingerprints in the cosmic microwave background, subtle ripples in the afterglow of the Big Bang. Others hunt for the gravitational waves they might produce while vibrating through space. If we ever confirm their existence, it wouldn't just rewrite the story of black holes. It could reveal that the universe is woven with structures far stranger than anything we've ever imagined. So while cosmic strings remain speculative, they remind us just how creative the cosmos might have been in its infancy. From snapping space-time threads to hidden dimensions, these ideas push the limits of physics and prove that when it comes to black holes, reality could be wilder than fiction. Some black holes in the early universe might have cheated, skipping the tedious process of star formation entirely and jumping straight into existence as cosmic behemoths. This is the direct collapse model, where unimaginably massive clouds of pure gas, dense and hot enough to defy the usual rules, crumpled directly into black holes without ever lighting up as stars. Picture the infant universe just a few 100 million years after the Big Bang. Vast reservoirs of hydrogen and helium, untouched by heavier elements, swam through the darkness. Under the right conditions, no competing stars nearby, no disruptive radiation, these pristine gas clouds could have grown unstable, their cores heating up to tens of thousands of degrees until gravity took over in a catastrophic runaway collapse. In mere thousands of years, they'd implode into black holes millions of times heavier than our Sun, the perfect seeds for today's supermassive monsters. What makes this process so special is the absence of metals, what astronomers call elements heavier than hydrogen and helium. In a normal star-forming region, metals cool the gas, allowing it to fragment into smaller clumps that birth many modest-sized stars. But without those cooling agents, the gas stays smooth and monolithic, collapsing all at once into a single, insatiable gravitational pit. These direct collapse black holes would have had a head start, feasting on surrounding gas to balloon into supermassive sizes long before ordinary star-born black holes could catch up. That might explain how we see quasars, bright disks of material swirling around supermassive black holes, shining in the universe when it was less than 1 billion years old. Their existence defies slower formation models, making direct collapse one of the most compelling solutions to the supermassive black hole mystery. Of course, this requires a cosmic Goldilocks scenario, regions with just the right density, just the right lack of metals, and just the right isolation to trigger such an extreme event. Telescopes like the James Webb Space Telescope are now hunting for these rare environments in the distant universe, where ancient light carries whispers of the first black hole nurseries. If we find them, it could rewrite our understanding of how the universe's most terrifying objects got their start, not from the death of stars, but from the raw chaos of gas itself. Supercomputers have given us a virtual time machine, allowing scientists to rewind the cosmos and witness how direct collapse black holes might have emerged in the chaotic early universe. These simulations reveal a delicate cosmic dance where ultraviolet radiation plays a starring role. In the darkness of the first few 100 million years, massive young stars would have flooded their surroundings with intense UV light, sterilizing nearby gas clouds and preventing them from cooling and fragmenting into smaller stars. Without this cooling, the remaining hydrogen and helium could stay hot and smooth, concentrating into a single, unstable behemoth. One groundbreaking simulation, run on some of the world's most powerful supercomputers, showed how a pristine gas cloud, untouched by heavier elements, could collapse directly into a black hole tens of thousands of times the mass of our Sun. The key was the absence of metals. Without them, the gas couldn't radiate away its heat efficiently, meaning it never broke apart into smaller clumps. Instead, it spiraled inward in a violent, single-minded plunge, forming a black hole in a cosmic blink. But there's another twist: the surrounding environment had to be just right. Too much turbulence or nearby starlight could disrupt the process, scattering the gas before it could collapse. Simulations suggest these perfect conditions might have been rare, but in a universe as vast as ours, even rare events could have seeded enough direct collapse black holes to explain the supermassive giants we see today. The latest models even hint at how these black holes could grow so quickly. Once formed, they'd sit at the heart of dense gas reservoirs, feasting on their surroundings with terrifying efficiency. Some simulations show them doubling in mass in just a few million years, fast enough to match the timeline of the universe's earliest quasars. It's a vivid reminder that the cosmos has shortcuts, ways to build monsters without waiting for stars to die. Every new simulation brings us closer to understanding whether direct collapse isn't just possible but inevitable, a hidden chapter in the story of how darkness first took hold of the universe. Here's a fresh cosmic mystery. What if dark matter, the invisible glue holding galaxies together, wasn't just lurking in the shadows but actively creating black holes? Some theorists propose that in the universe's densest early regions, dark matter particles might have collided with such violent energy that they triggered catastrophic implosions, birthing black holes out of pure annihilation. Imagine the early cosmos packed with clumps of dark matter regions where these mysterious particles piled up so thickly that they began smashing into one another, releasing enough energy to warp spacetime itself. Under the right conditions, these collisions could have become so intense that gravity took over, collapsing the entire region into a singularity. No stars, no gas, just raw dark matter igniting a black hole from the sheer force of its own destruction. But here's why this idea stirs debate. Dark matter, by definition, barely interacts with normal matter or even itself. For annihilation to birth black holes, these particles would need to collide far more often than most models suggest. Plus, if this process happened frequently, we'd expect to see its fingerprints everywhere: strange gamma-ray signals, distorted galaxy formations, or an overabundance of ancient black holes. Yet so far, the evidence is silent. Detractors argue it's a stretch, but supporters counter that certain exotic dark matter candidates like WIMP or primordial black holes themselves could have just the right properties to make it possible. Simulations show that in extreme environments like the centers of nascent galaxies, densities might have been high enough to tip the scales. It's a cosmic what if that challenges not just how black holes form, but what dark matter truly is. Until we catch dark matter in the act, though, this theory remains a tantalizing ghost, a shadow of a possibility lurking at the edge of physics. At the smallest scales imaginable, the fabric of spacetime isn't smooth. It's a seething, frothing chaos known as quantum foam. This isn't just poetic language. It's a prediction of quantum gravity, where the very foundations of reality churn with tiny, unpredictable fluctuations. And in this turbulent sea, microscopic black holes might be popping in and out of existence like bubbles in a boiling pot. These quantum black holes wouldn't last long thanks to Hawking radiation. They'd vanish almost instantly, evaporating in a burst of energy. But in the extreme conditions of the early universe, where densities and temperatures were unimaginably high, they might have had a shot at survival. Some theories suggest these fleeting black holes could have merged or captured enough energy to stick around, growing into the seeds of larger cosmic monsters. What's fascinating is how this idea ties into our quest for a theory of quantum gravity, a framework to unite Einstein's relativity with the bizarre rules of the quantum world. If spacetime itself can spontaneously birth black holes at tiny scales, it implies a deeper, wilder reality beneath the universe we see. Some models, like loop quantum gravity or string theory, even predict specific signatures for these events, subtle space-time ripples or unique radiation patterns we might one day detect. But here's the catch: observing quantum foam black holes directly is nearly impossible with current technology. Their microscopic size and fleeting existence put them beyond the reach of even our most sensitive instruments. Instead, scientists look for indirect clues, anomalies in particle collisions, unexpected energy spikes in cosmic rays, or even distortions in the cosmic microwave background. Some experiments at the Large Hadron Collider have searched for traces of these evanescent black holes, hoping to catch a glimpse of quantum gravity in action. While the evidence remains elusive, the mere possibility reshapes how we think about the universe's infancy. If space-time itself was once so unstable that black holes bubbled up spontaneously, it could mean our cosmos was born from a quantum storm, a place where the rules of physics as we know them didn't just bend but shattered entirely. And that's a mystery worth chasing to the very edges of reality. There's another way the universe might have cooked up its first black holes, not from collapsing stars or clumps of dark matter, but from the very energy field that sparked the Big Bang's explosive expansion. Picture the infant universe undergoing inflation, that trillionth of a second growth spurt when space itself stretched faster than light. The engine behind this frenzy was the inflaton field, a mysterious quantum force that eventually decayed, releasing its pent-up energy to form matter and radiation. But what if this decay wasn't perfectly smooth? Like a pot of boiling water cooling unevenly, pockets of the inflaton field could have collapsed violently under their own density, instantly transforming into black holes. These wouldn't be your typical stellar remnants. Inflaton-born black holes would carry the fingerprints of the universe's most primordial physics, forged before stars or even atoms existed. Some models suggest they'd have masses all over the map, from microscopic specks to colossal giants, depending on how and where the field fragmented. And here's where it gets surreal. If inflation truly birthed countless bubble universes within a multiverse, as some theories propose, these black holes might be relics of other cosmic birthing events tangled up in our own. The implications ripple through modern cosmology. If inflaton black holes exist, they could solve puzzles like dark matter or the bizarre seeds of supermassive black holes in the early cosmos. But proving it, that's the real challenge. Unlike star-formed black holes, these wouldn't be surrounded by the usual stellar wreckage. They'd be nearly pristine, hiding in the void. Some researchers hunt for their gravitational wave echoes or subtle distortions in the cosmic microwave background, while others simulate the chaotic end of inflation, searching for the exact conditions that could spawn them. Whether this theory holds up or not, it's a thrilling reminder of how black holes might be more than just cosmic vacuum cleaners. They could be time capsules, preserving the universe's wildest moments before time even worked the way we know it. And if we ever find one, it wouldn't just rewrite astronomy textbooks, it might crack open the door to realities beyond our own. Before stars filled the cosmos with heavy elements, before galaxies took shape, the universe was lit by a generation of stars so enormous, they make today's supergiants look like candles in comparison. These were population 3 stars, the first furnaces of creation, forged from the pure hydrogen and helium of the Big Bang. Without heavier elements to help them cool and stabilize, these titans burned ferociously and died young, collapsing into black holes that seeded the cosmos with darkness. Picture a star hundreds of times more massive than our Sun, shining with a brilliance that could outshine entire galaxies, but this glory was fleeting. With no metals to regulate their nuclear reactions, these behemoths exhausted their fuel in just a few million years, a cosmic blink compared to the Sun's 10 billion-year lifespan. Their deaths weren't gentle supernovas but catastrophic implosions, vanishing so completely that even light couldn't escape. The result? black holes with masses tens or even hundreds of times greater than anything formed from modern stars. The problem is, we've never actually seen one of these primordial giants. Their brief lives ended before galaxies fully assembled, leaving their remains drifting in the void. Without heavy elements to mark their deaths with bright stellar ejecta, their black hole descendants are nearly invisible to telescopes, but astronomers aren't giving up. The James Webb Space Telescope peers into the deepest reaches of time, searching for traces of their ultraviolet glow in the earliest epochs. Others study oddball black holes in our cosmic backyard, ones with masses too large to fit conventional star death models as possible relics of this first stellar generation. What makes this theory so compelling is its elegance. The first stars, by the sheer inevitability of physics, would have sown the universe with black holes. They were the pioneers, the ones that transformed the pristine cosmos into something richer, more complex. And if we can ever find their remnants, it would be like uncovering fossils from the universe's first dawn, proof of how darkness began its reign. Astronomers are on a cosmic treasure hunt, searching for the remnants of those first-generation stars' population, 3 black holes hidden in the darkness of deep space. Without the chemical fingerprints of later stars, these ancient objects are nearly invisible, but their gravity leaves subtle clues. One key method involves gravitational microlensing, when a black hole's immense gravity bends the light of a background star, briefly magnifying it like a cosmic magnifying glass. Telescopes scan millions of stars, waiting for those telltale flickers that betray an invisible passerby. But microlensing isn't the only strategy. Some teams study rogue gas clouds drifting near the Milky Way's halo, clouds with strange, turbulent motion that could hint at an unseen black hole's gravitational pull. Others examine ultra-fast, moving stars' stellar speedsters that may have been slingshotted by an encounter with one of these primordial relics. Even the faintest X-ray glows from isolated patches of space could signal a dormant black hole slowly feeding on wisps of interstellar gas. The James Webb Space Telescope adds another layer to the hunt. By peering into the distant universe, it captures the faint light of ancient quasars, bright disks of material swirling around supermassive black holes. Some of these quasars might be powered by population 3 remnants that grew monstrous over time, offering indirect evidence of their origins. Meanwhile, simulations refine the search, predicting where these black holes might lurk based on the evolution of the early cosmos. It's a detective story written in gravity and light, one that could rewrite our understanding of how the universe's first stars shaped the darkness we see today. Every flicker, every warp in motion, brings us closer to uncovering these elusive ghosts from the dawn of time. Now, let's venture into a realm where black holes don't come from stars, gas, or even quantum foam, but from the universe itself undergoing a cosmic metamorphosis. Picture the early cosmos, still a seething cauldron of energy, as the fundamental forces we know today, gravity, electromagnetism, and the nuclear forces, were once unified into a single, all-encompassing superforce. As the universe expanded and cooled, this symmetry shattered in a dramatic phase transition, like water freezing into ice. But what if this shift didn't happen smoothly? What if pockets of the old, high-energy state lingered like stubborn bubbles in a cooling pot until they suddenly collapsed, warping spacetime so violently that they birthed black holes in an instant? This isn't just speculation, it's grounded in some of the most ambitious theories in physics, like grand unification. These models suggest that as the universe transitioned from one state to another, regions of false vacuum could have formed. Think of these as cosmic defects, remnants of the earlier, more energetic era trapped in a higher energy state than their surroundings. And when these unstable pockets finally decayed, the energy released would have been so concentrated that gravity took over, crushing them into singularities. The scale of these black holes would depend entirely on when the phase transition occurred. If it happened early enough, they could range from microscopic to monstrous. Some might have evaporated almost immediately via Hawking radiation, while others could have survived long enough to become the seeds for supermassive black holes we see today. But here's where it gets even wilder. If this process happened, it wouldn't just explain black holes, it could leave ripples in spacetime itself. Gravitational wave observatories might one day detect the echoes of these ancient collapses, a fossilized imprint of the universe's violent growing pains. And if we're lucky, these signals could reveal which grand unified theory, if any, describes reality's deepest rules. Of course, proving this requires crossing a daunting gap between theory and observation. Phase transitions in the early universe leave no ordinary traces, no light, no heat signatures, just the gravitational aftershocks of their catastrophic decay. Yet as detectors grow more sensitive and simulations more precise, we might finally catch a whisper from an era when the cosmos itself was rewriting the rules, forging black holes not from matter, but from the raw energy of its own transformation. What if black holes aren't just cosmic objects but projections, like holograms cast from the very edges of reality? This is the staggering idea behind the holographic principle, a theory suggesting that all the information in our three-dimensional universe might actually be encoded on a two-dimensional surface at its boundary. And if that's true, black holes could be the universe's way of folding that information back into itself, creating gravitational whirlpools where the fabric of space and time becomes a tangled code. Think of it like a movie screen. The images appear three-dimensional, but they're really just flat projections of light. In the holographic universe, black holes might work similarly. Their immense gravity and swirling event horizons could be the physical manifestation of information crammed onto a distant cosmic screen. The math behind this is dizzying, but the implications are even wilder. Every particle falling into a black hole might not vanish, but instead get rewritten onto this boundary, like data being compressed onto a hard drive. For black hole formation, this changes everything. Instead of collapsing stars or quantum fluctuations, their birth could be tied to how information organizes or overloads on this cosmic horizon. Too much data crammed into one region of the code might warp spacetime so severely that it buckles into a singularity. It's as if the universe itself has a safety valve, and black holes are the emergency releases for information storage. Philosophically, this flips how we view reality. If black holes are holograms, then their interiors, the classic point of no return, might not even exist as physical space. Instead, what we perceive as a bottomless pit could just be a flaw in how we decode the universe's projection. Some physicists argue this solves the infamous black hole information paradox, ensuring no data is ever truly lost. Others counter that it turns existence itself into an illusion, a shadow play on the edge of something far stranger. Experiments are already testing pieces of this puzzle. Quantum entanglement studies, simulations of emergent spacetime, and even analyses of the cosmic microwave background hunt for glitches that might reveal a holographic universe. While the evidence isn't conclusive yet, the mere possibility reshapes not just how black holes form, but what they fundamentally are: not objects, but messages written in gravity's ink waiting to be decoded. What if black holes aren't just three-dimensional objects but cosmic knots tied in hidden dimensions we can't even see? This wild possibility comes from theories like string theory, which suggest our universe might have more than the familiar four dimensions of space and time. In this higher dimensional landscape, black holes could form in ways that defy everything we thought we knew about gravity. Imagine space as a vast, invisible fabric, except this fabric isn't flat. It's riddled with tiny, curled-up dimensions, folded so small they're impossible to detect. Under extreme conditions, like the heat of the early universe, these hidden dimensions could have twisted and warped, creating regions where gravity became so concentrated that it punched holes right through spacetime. The result: black holes born not from collapsing stars, but from the geometry of reality itself unraveling. One version of this idea comes from brainworld cosmology, which paints our universe as a floating membrane or brain in a higher dimensional space. If two of these brains collided in the early cosmos, the energy released might have been enough to trigger black hole formation instantly, no stars required. These objects would carry fingerprints of those extra dimensions, potentially behaving in ways that break Einstein's rules. Scientists aren't just speculating, they're testing this at the Large Hadron Collider. By smashing particles together at nearly light speed, they hope to create microscopic black holes that would evaporate in a flash. If these fleeting holes appear, their properties could reveal whether extra dimensions exist. So far, no luck, but the hunt reshapes what's possible, reminding us that black holes might be more than cosmic vacuum cleaners. They could be portals to the universe's deepest secrets, waiting in dimensions beyond our sight. In the crowded chaos of the young universe, collisions weren't just common, they were inevitable. Among the most dramatic were the smash-ups between neutron stars, the dense corpses of dead stars, packing a sun's worth of mass into a city-sized sphere. Today, these mergers are rare cosmic spectacles, but back then, they might have been almost routine, creating black holes in a way modern astronomy rarely witnesses. Picture the cosmos just a few 100 million years after the Big Bang, packed with stars living fast and dying young. When these stars exploded as supernova, many left behind neutron stars, objects so dense, a teaspoon of their material would weigh billions of tons. In such a tightly packed environment, these stellar remnants wouldn't drift alone for long. Gravitational tugs from nearby objects could send them spiraling toward one another, culminating in violent mergers. If the combined mass crossed a critical threshold, the neutron stars wouldn't just form a heavier neutron star, they'd collapse directly into a black hole. Gravitational wave observatories like LIGO and Virgo have given us a front-row seat to modern neutron star collisions. The 2017 detection of two neutron stars merging, an event that shook space-time and glittered with gamma rays, showed how these crashes can create black holes under extreme conditions. But in the early universe, the recipe was different. With higher densities and more frequent interactions, mergers would have happened faster, more often, and with less warning. Some simulations suggest these ancient smash-ups could have birthed black holes faster than star collapse alone, seeding the cosmos with singularities long before modern galaxies took shape. Yet there's a puzzle. If early neutron star mergers were so prolific, why don't we see more evidence in gravitational wave data? Part of the answer might lie in time. The black holes formed from these ancient mergers would have had billions of years to drift, grow, or merge again, leaving few traces of their violent origins. Others may have been too light to survive to the present day, evaporating through Hawking radiation. But as detectors become more sensitive, scientists are combing through gravitational wave signals for anomalies, odd masses, or spins that could hint at these primordial collisions. This theory bridges two cosmic eras, the frantic, crowded youth of the universe and the quieter, more spread-out cosmos we see today. It's a reminder that black holes might not always form in isolation. Sometimes they're born from chaos, forged in the wreckage of stars that couldn't escape each other's pull. And if we're lucky, the next ripple in space-time might carry echoes of that ancient violence, revealing how the universe's first black holes grew from the ashes of its first stellar dances. Some of the most bizarre black holes might not come from dying stars or colliding neutron stars, but from the very fabric of reality itself crumbling apart. This is the mind-bending theory of vacuum decay, where the universe could suddenly drop into a lower energy state like a ball rolling downhill, and in the process unleash black holes as cosmic shrapnel. Think of space as a landscape filled with valleys and hills, where each valley represents a possible stable state for the universe. Right now, we're sitting in one of those valleys, a stable, predictable place where physics works the way we know it. But what if our valley isn't the lowest possible point? quantum mechanics allows for the possibility that somewhere out there, a tiny bubble of true vacuum could form, a region where the universe's energy drops to an even lower state. If this bubble expanded at light speed, it would rewrite the laws of physics in its path, and along the way, the violent transition could twist space-time so drastically that black holes erupt into existence. These black holes wouldn't form from matter collapsing, but from sheer energy-like cracks forming in ice as it freezes. The math suggests they'd be microscopic at first, but in the frenzy of a vacuum decay event, countless such singularities could pepper the cosmos. And if this happened today, the consequences would be apocalyptic. Entire galaxies could be shredded as the new vacuum state erased the old laws of physics, with black holes forming like scars in the wake of destruction. The silver lining: if vacuum decay has already happened anywhere in the universe, we'd likely see its deadly wave front coming, though with zero ability to stop it. Thankfully, most physicists consider this scenario vanishingly unlikely in our current epoch. The universe seems remarkably stable, and no telltale bubbles of doom have shown up in 13.8 billion years. But the possibility lingers, a ghostly reminder that black holes might not just be part of the cosmic order, they could be the aftershocks of reality itself resetting. Until we fully understand the nature of the vacuum we live in, it remains one of the most unsettling and fascinating black hole origins of all. Now let's tackle one of the most intriguing what-ifs in black hole physics. What if singularities, those infinitely dense points at the heart of black holes, were too dangerous for the universe to leave exposed? This is the essence of Roger Penrose's cosmic censorship hypothesis, a bold idea suggesting black holes evolved as nature's way of quarantining singularities, keeping their destructive math locked behind event horizons where they couldn't wreak havoc on reality. Imagine the early universe as a delicate tapestry, its structure smooth and predictable, but without black holes, naked singularities without the protective cloak of an event horizon might have dotted this tapestry like cosmic landmines. At these points, gravity would spiral out of control, space-time would tear, and the laws of physics as we know them would simply break. Penrose argued that nature abhors such chaos. So, black holes formed as cosmic censors, their event horizons acting like containment shields, ensuring singularities stayed hidden and the universe remained governable by known physics. The elegance of this idea lies in its simplicity. If true, it means black holes aren't just accidents of collapsing stars, they're necessary. Without them, the universe's infancy could have been riddled with unpredictable gravitational storms, making structure formation impossible. Think of it as a cosmic failsafe. The moment matter collapses too far, an event horizon snaps into place like a safety net, preventing the singularity from spilling its chaos into the wider cosmos. But not everyone's convinced. Some theorists point to hypothetical scenarios like colliding black holes or extreme spin that might briefly expose a singularity before nature corrects the breach. Others argue that quantum gravity, once fully understood, could rewrite the rules entirely, rendering singularities less catastrophic than classical physics predicts. For now, cosmic censorship remains a tantalizing, unproven guardian of cosmic order. It's a reminder that black holes might be more than just gravity's dead ends. They could be the universe's meticulous editors, scrubbing out the equations that would otherwise make reality impossible. And if Penrose is right, we owe the stability of the cosmos to these dark sentinels standing guard over the abyss. Deep in the equations of supersymmetry, a dazzling theoretical framework where every known particle has a hidden, heavier twin, lies a radical idea. The universe's first black holes might not have come from stars or quantum chaos, but from a shadowy family of particles so massive they collapsed under their own weight. Supersymmetry, or SUSY for short, proposes a cosmic symmetry so perfect that it doubles the number of particles in nature. For every quark, there's a squark. Every electron has a selectron. And most crucially, some of these superpartners could be staggeringly heavy, so dense that if they clumped together in the early universe's frenzy, they might have crumpled space-time into black holes without any stars involved. Here's how it could have worked. Moments after the Big Bang, when the cosmos was smaller and hotter, sussy particles might have been abundant. Some models suggest they'd behave like ultra-dense dark matter, gathering into vast clouds. If enough of them pooled in one region, their combined mass could have crossed a critical threshold, gravity winning out, birthing black holes as effortlessly as raindrops forming in a storm. But there's a catch. If sussy black holes exist, we'd expect their fingerprints everywhere, yet experiments at the Large Hadron Collider have found no trace of superpartners despite decades of searching. Each null result tightens the constraints, forcing theorists to rethink. Maybe sussy particles are too elusive for current colliders, or perhaps they decayed too fast in the early cosmos to leave relics. Still, the possibility lingers like a ghost in the math. Some researchers hold out hope that future detectors, or even cosmic ray observatories, might spot a rare sussy particle collision, one that mimics the fleeting signatures of microscopic black holes. Others argue that even if sussy isn't the answer, the idea reshapes our thinking. Black holes might not need stars or singularities to form. Sometimes the right kind of particle is all it takes to bend reality to its breaking point. For now, supersymmetric black holes remain suspended between theory and observation, a tantalizing what if in the quest to understand how darkness first took hold of the universe. Whether they're real or just mathematical mirages, they remind us that the cosmos has more tricks up its sleeve than we've ever dreamed. At scales so small they make atoms look gigantic, the universe might have been fizzing with black holes born from pure quantum chaos. This is the staggering realm of Planck-scale physics, where space and time themselves become grainy, uncertain, and prone to violent fluctuations. If you shrunk down 1 billion times smaller than a proton, you'd reach the Planck length, the universe's ultimate pixel size, where gravity and quantum mechanics clash in ways we barely understand. And in that microscopic storm, black holes could have popped into existence like bubbles in a boiling sea. Loop quantum gravity, one of the boldest theories aiming to unite relativity and quantum mechanics, paints space as a woven fabric of tiny, indivisible threads. In this framework, the fabric isn't smooth but made of spin foam, a frothing network where loops twist and intersect. Under enough strain, these threads could snap or knot, pinching spacetime into microscopic black holes without any matter involved. It's like twisting a rubber band until it suddenly knots itself, except here, the rubber band is reality's underlying structure. These Planck-scale black holes wouldn't last long. Thanks to Hawking radiation, they'd vanish almost instantly, evaporating in bursts of energy. But in the ultra-dense early universe, their fleeting existence might have left fingerprints. Some models suggest they could have seeded larger black holes by merging or acting as gravitational anchors for collapsing gas. Others propose their evaporations might have triggered subtle ripples in the cosmic microwave background, ghostly echoes of quantum gravity's first experiments. The challenge, directly observing phenomena at the Planck scale, is like trying to hear a whisper in a hurricane. Our most powerful particle colliders operate at energies trillions of times too weak to probe these depths. Yet theorists aren't giving up. Some hunt for indirect clues in high-energy cosmic rays or anomalies in gravitational wave data. Others simulate spin foam dynamics, tracing how quantum spacetime might fold into black holes under extreme conditions. What makes this idea so compelling isn't just its audacity. It's the possibility that black holes aren't cosmic accidents, but inevitable byproducts of how reality stitches itself together at the smallest scales. If Planck-scale physics truly forged black holes in the universe's first moments, they'd be more than just objects. They'd be quantum gravity's graffiti, scrawled across the cosmos in spacetime itself. What if black holes weren't just cosmic vacuum cleaners, but the hidden architects of dark energy itself? This radical theory suggests that the mysterious force accelerating the universe's expansion might trace back to the very first black holes and how they evaporated. Picture the early cosmos teeming with tiny black holes popping in and out of existence like quantum fireworks. According to Hawking radiation, these micro-black holes wouldn't last forever. They'd slowly leak energy until vanishing in a final burst. But here's the twist. That evaporation process might have left behind a faint, persistent energy field, woven into the fabric of space itself. Over billions of years, as countless black holes faded away, their collective influence could have grown into the repulsive force we now call dark energy. This idea ties into one of physics' biggest headaches, the cosmological constant problem. Quantum theory predicts that empty space should bubble with wild, uncontrollable energy, yet the observed dark energy is shockingly weak. If evaporating black holes fine-tuned this balance, acting as cosmic pressure valves that bled off excess energy, it could explain why the vacuum of space isn't infinitely more explosive. The math gets slippery, though. Critics argue that Hawking radiation alone doesn't produce the right kind of energy to drive dark energy's smooth, uniform push. But alternative models suggest early black holes might have twisted spacetime in subtler ways, perhaps by imprinting quantum information onto the universe's horizon, altering how space itself stretches over time. Others propose that black hole mergers stirred up gravitational waves so vast they subtly stretched the cosmos from within. While definitive proof remains elusive, this theory reframes black holes as more than just gravity's dead ends. They could be cosmic sculptors shaping not just galaxies but the fate of the universe itself. And if future telescopes catch echoes of ancient black hole explosions in the cosmic microwave background, we might finally crack one of cosmology's deepest mysteries: why the void isn't empty at all, but humming with invisible energy. The early universe wasn't just hot and dense, it might have been lumpy, riddled with invisible fault lines where the very laws of physics changed abruptly. These cosmic cracks, known as domain walls, were like borders between patches of reality where fundamental forces behaved differently. And when these walls crashed together, they could have unleashed something terrifying. Black holes born not from matter, but from the raw energy of the universe's broken symmetry. Picture space just after the Big Bang, cooling from an unimaginable frenzy. As it settled, quantum fields organizing themselves like ice crystals freezing in water, but not uniformly. Some regions froze into one configuration, others into another, leaving boundaries between them where the rules shifted suddenly. These were the domain walls, sheets of concentrated energy thinner than an atom but stretching across light years. Most theories suggest they decayed fast, but if even a few survived long enough to collide, the sheer tension in those crashes could have crumpled spacetime into black holes in an instant. The math is mind-bending. When two domain walls intersect, their energy doesn't just cancel out, it concentrates at the impact point, warping gravity so intensely that a singularity forms. No star death, no gas collapse, just pure, violent geometry birthing a black hole from the wreckage of cosmic order. What's wild is that these objects would carry a signature of that primordial chaos. Their spins or masses might reflect the angle of collision, offering clues about the universe's first fractures. And here's where it gets even stranger. If domain walls were unevenly distributed, their black hole offspring could have stamped the cosmos with weird, large-scale patterns. Astronomers call this cosmic anisotropy, subtle variations in the universe's structure that might trace back to these ancient defects. Some researchers even speculate that the mysterious cold spot in the cosmic microwave background, a patch of sky oddly devoid of radiation, could be the ghost of a domain wall collision billions of years ago. Of course, proving this is a challenge. Domain walls would have dissolved early, leaving no obvious traces beyond their hypothetical black holes. But next-generation telescopes scanning the cosmic microwave background for irregularities, or gravitational wave detectors catching echoes of oddly oriented black hole mergers, might one day spot the fingerprints of these cosmic scars. Until then, it's a thrilling reminder that black holes might not just be traps for matter. They could be monuments to a time when the universe itself was still figuring out its own rules. There's a temperature so extreme it doesn't just melt matter, it transforms it. In particle physics, this is called the Hagedorn temperature, a theoretical limit where protons, neutrons, and even quarks lose their identities, dissolving into a seething soup of pure energy. But here's the twist. In the early universe's furnace-like conditions, this same chaos might have forged black holes without a single star collapsing. Think of the Hagedorn temperature as nature's ultimate pressure cooker. Beyond this point, around 2 trillion degrees, normal matter can't exist in any recognizable form. Particles don't just collide, they multiply endlessly, creating an explosive cascade of energy. Now rewind the clock to the first microseconds after the Big Bang, when the entire cosmos was this hot. In that inferno, pockets of ultra-dense plasma could have crossed a critical threshold, their energy so concentrated that gravity overwhelmed all other forces. Instead of forming new particles, these regions might have collapsed directly into black holes, like bubbles of space-time boiling over into darkness. The math behind this is as elegant as it is unsettling. At Hagedorn temperatures, matter stops behaving predictably. The usual rules of particle interactions break down, and entropy, the measure of chaos in a system, skyrockets. Under these conditions, black holes aren't just possible, they might have been inevitable. Some models even suggest these primordial black holes would have had a unique mass distribution, clustering around a specific size dictated by the Hagedorn limit itself. What's fascinating is how this theory bridges particle physics and cosmology. If correct, it means black holes weren't just born from dying stars or quantum fluctuations. They could be relics of matter's ultimate phase transition, fossils from the moment the universe was too hot for particles to even exist. While we can't recreate Hagedorn temperatures in labs yet, experiments at the Large Hadron Collider edge close enough to probe how matter behaves at extreme energies. And if traces of these black holes linger in gravitational wave data or the cosmic microwave background, they'd offer a glimpse into a time when the universe was so hot, it cooked reality itself into something entirely new. This isn't just about how black holes form, it's a window into the universe's most extreme state, where the very idea of matter loses meaning. And if Hagedorn temperature black holes are out there, they're not just cosmic oddities. They are reminders that under enough heat and pressure, even the fabric of reality can bend until it snaps. Here's an idea that bends time itself. What if black holes aren't just gravitational monsters but colossal time crystals, structures that repeat in time like a cosmic heartbeat? Time crystals are one of modern physics' strangest discoveries, systems that oscillate endlessly without energy input, breaking time's symmetry just by existing. In labs, we've created tiny versions using chains of ions or superconducting qubits, but in the early universe, black holes might have been nature's ultimate time crystals, their rhythms shaping the cosmos. Picture the event horizon of a black hole not as a static boundary, but as a pulsating surface, cycling through quantum states with perfect regularity. Just as a time crystal repeats its pattern in time rather than space, a black hole's internal dynamics could oscillate predictably, its gravitational field, spin, or even information distribution ticking like a cosmic clock. Some models suggest this periodicity might have left imprints on the early universe's structure, subtly influencing how galaxies clustered or gravitational waves rippled outward. The math behind this is dizzying, but the implications are even wilder. If black holes are time crystals, their oscillations could solve lingering mysteries like why supermassive black holes align so precisely across billions of light years, or how information escapes a black hole's grip without violating quantum laws. Their rhythmic behavior might even hint at deeper symmetries in quantum gravity, bridging relativity and the quantum world in ways we've yet to fathom. Of course, skepticism abounds. Critics argue that time crystals require finely tuned conditions impossible for astrophysical objects. Yet supporters counter that black holes, with their quantum gravitational weirdness, might operate by rules we're only beginning to glimpse. Future gravitational wave detectors could hunt for these telltale oscillations, hidden frequencies in the hum of merging black holes that betray their crystalline hearts. Whether this theory holds or not, it reframes black holes as more than cosmic traps. They might be time's keepers, their rhythms echoing from the dawn of creation, a reminder that even in the darkest corners of the universe, order persists, ticking silently against the void. Now consider this: what if black holes didn't just form from ordinary matter, but from something far stranger lurking in the universe's primordial soup? Enter exotic matter, hypothetical particles so bizarre their very existence bends the rules of physics. Among them, cue balls and strangelets stand out, cosmic oddities that could have collapsed into black holes under the extreme pressures of the early cosmos. Cue balls are theoretical blobs of squished-together matter, not made of protons or neutrons, but held together by an entirely new kind of quantum force. Picture them as bubbles of pure energy, dense enough to warp spacetime around them. In the early universe's frantic energy bath, these cue balls could have clumped together until their collective gravity became unstoppable, triggering a runaway collapse straight into a singularity, no star required. Then there are strangelets, fragments of strange matter, a hypothetical state where quarks, the building blocks of protons and neutrons, rearrange into something far denser and more stable. If strangelets existed in the universe's first moments, even a tiny speck could have acted like a cosmic seed, pulling in surrounding matter with such ferocity that it snowballed into a black hole. Unlike ordinary matter, strangelets wouldn't need immense pressure to collapse. Their inherent density might have made them ticking time bombs, destined to implode under their own weight. The implications are mind-bending. If exotic matter spawned black holes, they'd be fundamentally different from the ones we know, smaller, denser, or with quantum properties we've never observed. Some theories even suggest they could still be drifting through space today, invisible yet detectable through subtle ripples in particle collisions or gravitational microlensing surveys. Of course, proving this is a monumental challenge. Exotic matter remains purely hypothetical. No lab has ever confirmed its existence, but experiments at facilities like the Large Hadron Collider hunt for traces of these particles, while astrophysicists scour ancient neutron stars for hints of strangelet contamination. It's a long shot, but if confirmed, it would rewrite black hole origins entirely. Whether exotic matter is a cosmic reality or just a fascinating what-if, it forces us to think bigger. The universe's first black holes might not have needed stars, gas, or even conventional physics, just a pinch of something utterly alien lurking in the chaos of creation. And that's a reminder that when it comes to black holes, reality might be far stranger than fiction. What if black holes aren't just cosmic objects, but the universe's way of overloading its own pixels? This wild idea comes from digital physics, a radical theory suggesting reality might not be smooth and continuous, but built from tiny, indivisible chunks of spacetime like the pixels on a screen. And if that's true, the first black holes could have formed when these cosmic pixels got too bright, crossing an energy threshold that made them collapse into singularities. Think of the early universe as an ultra-high-resolution grid, each cell humming with energy. Most of these cells stayed stable, quietly humming along as spacetime's building blocks. But in regions where energy spiked, perhaps from quantum fluctuations or cosmic inflation, individual pixels could have become so overloaded that they warped spacetime inward, pinching off into microscopic black holes. It's like a digital image glitching so hard the pixels tear holes in the screen itself. The math behind this is as elegant as it is strange. Just as your computer crashes if too much data floods one pixel, spacetime might have a built-in limit, a maximum energy density any single pixel can handle. Exceed that and gravity takes over, folding the pixel into a black hole. Some models even suggest these primordial pixel holes would have had predictable masses tied directly to the fundamental scale of the universe's resolution. Here's where it gets even wilder. If the universe is truly digital, these black holes wouldn't just be objects, they'd be errors, glitches in the cosmic code where the simulation, for lack of a better word, couldn't process the data fast enough. Their event horizons would act like firewalls containing the computational overload. It's a stretch, but it's also poetic. The darkest objects in existence might just be spacetime's way of rebooting corrupted sectors. Of course, proving this is a nightmare. Digital physics remains speculative, and no experiment has ever detected spacetime's pixelation. But some researchers hunt for hints in high-energy particle collisions, where microscopic black holes might flicker into existence if the universe's pixels are small enough. Others look for odd patterns in the cosmic microwave background, subtle pixel-like anisotropies that could betray reality's underlying grid. Whether this theory holds water or not, it reshapes how we see black holes. They might not be accidents of collapsing stars, but inevitable byproducts of a universe running on cosmic code where even darkness has a resolution limit. And if we ever find proof, it wouldn't just rewrite astrophysics, it'd reveal that existence itself is pixel perfect, down to its darkest corners. Imagine a universe where magnets don't come in pairs, where north and south poles exist completely separate, free to wander alone like cosmic ghosts. These are magnetic monopoles, particles predicted by grand unified theories to have formed in the searing heat of the early cosmos. And if enough of them clumped together, their sheer density might have warped spacetime into black holes without a single star ever dying. Monopoles are fascinating beasts, unlike the magnets in your fridge, always sporting both a north and south pole. These hypothetical particles would carry just one magnetic charge. Theory suggests they'd be incredibly massive, maybe even a quadrillion times heavier than a proton. In the first moments after the Big Bang, as the fundamental forces split apart, monopoles could have flooded the universe like cosmic shrapnel from that explosive divorce. But here's the puzzle. If monopoles were so abundant, why don't we see them today? This is the infamous monopole problem, and one solution is downright dramatic. If monopoles clustered tightly enough, their combined mass could have triggered gravitational collapse, squeezing them into black holes. Picture a swirling sea of these ultra-dense particles, pulled together by gravity until spacetime itself buckled under their weight. No need for stars or gas, just pure, concentrated magnetism birthing singularities. Some grand unified theories even suggest monopoles wouldn't just form black holes, they'd solve their own overproduction problem in the process. If most monopoles ended up trapped inside black holes, it would neatly explain their absence in the modern universe. These black holes would be unlike any others, carrying the imprint of a time when electromagnetism and gravity danced on the same razor's edge. The hunt for evidence is ongoing. Experiments deep underground search for lone monopoles passing through Earth, while particle colliders attempt to create them in fleeting high-energy collisions. So far, no luck, but if we ever spot one or detect ancient black holes with unusual properties, it could confirm that the universe's first darkness was forged not just by gravity, but by magnetism's lost orphans. Until then, monopoles remain one of physics' most tantalizing what-ifs, lurking at the intersection of theory and cosmic history. Deep in the quantum realm, where particles share invisible connections across vast distances, lies one of physics' most perplexing mysteries: entanglement. Two particles can become so deeply linked that changing one instantly affects the other, no matter how far apart they are. But what if this bizarre phenomenon didn't just influence tiny particles but shaped the very fabric of spacetime into black holes? The idea starts with a radical proposal called ER equals EPR. Physicists Leonard Susskind and Juan Maldacena suggested that entangled particles might be connected by microscopic wormholes, Einstein-Rosen bridges hidden in the quantum foam. In the early universe's chaos, where particles were packed together like grains of sand, these quantum threads could have tangled into dense knots, and when enough of them twisted together, space-time itself might have knotted into a singularity, birthing black holes from pure entanglement. Picture it like this. Imagine two entangled particles as opposite ends of a stretched rubber band. Normally, that band stays invisible, just a mathematical link. But under the extreme conditions of the early cosmos, countless entangled pairs could have woven a web so intricate that their collective gravity crumpled entire regions into black holes. These wouldn't be the black holes we know from collapsing stars, but something far stranger: quantum scars in spacetime, where information never really disappears, just gets scrambled across hidden wormhole networks. This isn't just wild speculation. Recent simulations in quantum gravity hint that entangled black holes could share wormhole-like connections, their event horizons acting like cosmic encryption devices. Some researchers even suggest that the universe's first black holes might still carry echoes of this quantum ancestry, perhaps explaining why we see correlations between distant black holes that defy classical physics. Critics argue the math is still in its infancy, and proving such a theory would require detecting quantum signatures in black hole mergers, something beyond today's technology. Yet the idea reshapes how we think about darkness in the cosmos. If black holes are quantum entanglement made visible, then the universe's first monsters weren't just gravitational traps but cosmic messengers, whispering secrets about the deepest links between quantum weirdness and the structure of reality itself. And if we're right, the next revolution in black hole science might not come from telescopes but from quantum labs, where scientists manipulate entangled particles to simulate spacetime's most mysterious knots. Because sometimes the universe's biggest secrets hide in the smallest connections. What if the universe's first black holes weren't forged from collapsing stars or quantum chaos, but from something far stranger, glitches in reality's cosmic projector? This is the holographic noise theory, and it suggests that black holes might be shadows of quantum turbulence on the very edge of existence. Picture the universe as a hologram, a three-dimensional projection encoded on a two-dimensional surface at its boundary. According to the holographic principle, all the information in our cosmos, every star, every galaxy, even you, is really just data etched onto this distant cosmic screen. But in the early universe, that screen wasn't perfectly smooth. Quantum fluctuations would have made it buzz with static, like interference on an old TV. Sometimes that static could have grown so intense, it warped the projection, pinching spacetime in the interior until black holes bubbled into existence. Think of it like pressing your finger into a stretched sheet of plastic wrap. The tension distorts the surface, creating a deep dent. In the holographic universe, quantum noise on the boundary might have done something similar, twisting spacetime until it collapsed into a singularity. These black holes wouldn't form from matter clumping together, but from information itself spiraling out of control. The math behind this is dizzying, but the implications are even wilder. If holographic noise spawned black holes, they'd carry unique signatures, specific masses or spins tied to the nature of the quantum fluctuations that birthed them. Some models even suggest their event horizons could encode information differently, like scrambled pixels in a corrupted image. Of course, testing this isn't easy. Holographic noise would have been faint, fleeting, almost impossible to detect directly. But scientists are hunting for echoes in the cosmic microwave background, where subtle irregularities might betray ancient turbulence on the universe's edge. Others simulate black hole mergers, searching for gravitational wave patterns that could hint at a holographic origin. Whether this theory holds or not, it reshapes how we see black holes. They might not just be cosmic vacuum cleaners, but glitches in the universe's code, reminders that reality's deepest truths could be written in quantum static, flickering at the edge of everything we know. Here's a concept so bizarre, it turns the entire universe into a cosmic slot machine. What if black holes weren't born from stars or quantum chaos, but from consciousness itself randomly flickering into existence? This is the Boltzmann brain paradox, a thought experiment so unsettling. It suggests that in an eternally expanding universe, random fluctuations could spontaneously assemble anything, even self-aware minds or black holes. Picture a universe stretching endlessly into the future, where particles drift further apart and entropy, the measure of disorder, keeps rising. Given enough time, even the most improbable events become inevitable. Atoms might randomly align to form a functioning brain, complete with false memories of a past that never existed. These hypothetical observers are called Boltzmann brains, freak accidents of entropy, conscious for just a fleeting instant before dissolving back into chaos. But here's the twist: the same random fluctuations that could spawn a mind might also create something far darker, a black hole. In this scenario, quantum jitters in the void could, by sheer chance, concentrate enough energy in one spot to warp spacetime into a singularity. No collapsing star, no cosmic collision, just a statistical fluke, like rolling a million dice and having them all land on 6 simultaneously. These Boltzmann black holes would be cosmic aberrations, vanishing almost instantly but leaving behind a chilling implication. If randomness can birth a black hole, how do we know our universe's black holes weren't forged the same way? Critics pounce on this idea quickly. The odds of a Boltzmann black hole forming naturally are astronomically low, far less likely than assembling a working brain. Yet supporters argue that in an infinite universe, impossible is just a matter of scale. Some even suggest these fluctuations could explain why we see supermassive black holes so early in cosmic history, if the universe got lucky with a few ultra-rare density spikes in its infancy. The real shocker: Boltzmann brains and black holes force us to confront an uncomfortable question. Is our universe's structure the result of inevitable physics or just a roll of the dice? For now, it's a paradox without resolution, a reminder that in the grand casino of existence, the house always wins. And if we ever find a black hole too old, too isolated, or too bizarre to fit conventional theories, we might have to ask, did gravity make it or did chaos? Now let's flip black hole physics inside out literally. If a black hole is a cosmic one-way street where nothing escapes, its theoretical opposite would be a white hole, a gushing fire hose of reality where matter and energy can only pour out, never in. The math allows for such objects, but no one's ever seen one unless they're hiding in plain sight as the universe's first black holes. Imagine the early cosmos as a turbulent sea of extreme physics, where white holes burst into existence like reverse fireworks, spitting out radiation and particles in violent eruptions. But here's the twist: in those frenzied conditions, a white hole might not have stayed a white hole for long. If it exhausted its energy or encountered a surge of incoming matter, the equations suggest it could collapse inward, its no entry sign flipping to no exit. The result: a black hole born not from collapse but from a failed rebirth. This isn't science fiction. Einstein's field equations treat black holes and white holes as two sides of the same coin. Some models even suggest that the Big Bang itself could have been a white hole event, with the infant universe exploding outward from a singularity. If smaller white holes formed in that aftermath, their deaths might have seeded the cosmos with black holes that inherited their exotic properties. The challenge: white holes are notoriously unstable. Like a car with no brakes running out of fuel, they'd likely sputter and invert under the slightest cosmic pressure. But in the universe's infancy, where extreme energies ruled, this instability could have been a feature, not a bug. A dying white hole wouldn't just vanish, it'd leave behind a gravitational scar, a black hole whispering secrets of its former self. Hints of this might lurk in the spins of ancient black holes. If they originated as white holes, their rotation could carry odd imprints, telltale glitches in their gravitational wave signals or unusual jet emissions. Others speculate that Hawking radiation, the slow leak of energy from black holes, might actually be a white hole's last gasp on a quantum scale, a faint echo of its inverted past. So while white holes remain elusive, their ghostly fingerprints could be all around us, woven into the fabric of black holes we've studied for decades. If true, it means the universe's first darkness wasn't just born from chaos, but from a failed explosion, a cosmic door that slammed shut and never opened again. Let's dive into one of the most mind-bending theories yet. What if black holes didn't form from matter or energy, but from information itself? Imagine the early universe as an overstuffed hard drive where the sheer density of data, every quantum state, every particle's position, reached a breaking point. Under that kind of pressure, space-time might have buckled, collapsing not just into stars, but into black holes as nature's ultimate storage solution. This idea comes from a radical blend of quantum mechanics and information theory. In simplest terms, the universe doesn't just contain information, it is information. Every particle, every force can be described as bits of data woven into the fabric of reality. Now rewind to the cosmos's first moments when everything was packed into a seething, ultra-dense hotspot. Calculations suggest there's a limit to how much information can occupy a given volume before the system can't process it anymore, like a computer freezing from too many open tabs. When that threshold was crossed, black holes might have formed as cosmic Control-Alt-Delete, compressing that overflow into singularities where information isn't lost, just locked away. The math behind this is staggering. Theoretical physicists like Jacob Bekenstein and Stephen Hawking showed that black holes have entropy, a measure of hidden information, and that their event horizons act like encrypted hard drives, trapping data in ways we don't fully understand. Some models take this further, suggesting that in the early universe's frenzy, regions of extreme information density could have collapsed under their own data weight, forming black holes without needing stars or even matter. Here's where it gets even wilder. If information compression spawned black holes, they wouldn't just be cosmic vacuums, they'd be archives, preserving the universe's earliest data in gravitational code. That could explain why we see supermassive black holes so early in cosmic history. They weren't built slowly, but emerged full-formed from the universe's need to manage its own overwhelming complexity. Of course, skeptics argue this pushes the analogy too far. After all, information isn't a physical substance. Yet supporters counter that at quantum scales, the line between data and reality blurs. Experiments in quantum gravity and simulations of holographic universes keep testing the limits, searching for ways information could warp spacetime itself. Whether this theory holds or not, it reshapes how we see black holes. They might not be accidents of collapsing stars, but inevitable byproducts of a universe trying to handle its own cosmic paperwork. And if that's true, the darkest objects in existence could be hiding the brightest keys to understanding reality's deepest rules, locked away, waiting to be decoded. Picture this: our universe isn't alone. It's just one bubble in an endless cosmic foam, where other universes drift like phantom islands in an unseen sea. Now imagine what happens when two of these bubbles collide. The energy at the point of impact would be unimaginable, a cosmic thunderclap so violent it could twist spacetime into black holes on contact. This isn't just wild speculation, it's a tantalizing possibility within multiverse theories. If our universe is part of a vast bubble bath of other realities, each with its own physical laws, then collisions between them wouldn't just be possible, they'd be inevitable. And when two universes brushed against each other in the early cosmos, The sheer force of that meeting could have concentrated gravity so intensely that singularities formed like cosmic scars at the crash sites. Think of it like two soap bubbles merging. Where their surfaces touch, the tension warps the thin film between them. Now scale that up to universes, except instead of soapy water, it's space-time itself buckling under the strain. The result, black holes birthed not from stars or quantum chaos, but from the raw friction of reality against reality. Some models suggest these collision-born black holes would carry distinct signatures, unusual spins, unexpected masses, or even traces of the other universe's physics encoded in their gravitational waves. If we could study one up close, it might reveal clues about the multiverse itself, like a fossilized imprint of a long-vanished cosmic neighbor. Of course, proving this is a monumental challenge. Direct evidence of other universes remains elusive, and their collisions would have left behind only subtle echoes, perhaps hidden in the cosmic microwave background or buried in the merger patterns of ancient black holes. But as gravitational wave detectors grow more sensitive and telescopes peer deeper into the early universe, we might one day catch a whisper of that primordial crash, a reminder that our universe's darkness might not be homegrown, but the legacy of a fateful encounter with another reality entirely. Whether this theory holds up or not, it stretches our imagination to the limit. Black holes might not just be cosmic accidents. They could be the bruises left behind when the multiverse itself bumped into something we're only beginning to dream of. Here's a fascinating twist. What if black holes aren't just gravity's dead ends, but the universe's original supercomputers? Picture the early cosmos as a system drowning in data, its quantum chaos growing too complex to handle. That's where black holes might have stepped in, not as destroyers but as cosmic processors crunching the numbers to keep reality from crashing. Think of the Big Bang's aftermath like a glitchy computer booting up. Space was packed with quantum fluctuations, particle collisions, and raw energy, so much information that the laws of physics risked overload. Enter black holes, acting like nature's compression algorithm. Their event horizons don't just swallow matter, they encode it, storing the universe's messy initial conditions in a format so dense, even light can't escape. In this view, singularities aren't abysses, they're hard drives, locking away the chaos to keep the cosmos running smoothly. This idea isn't just poetic, it's rooted in hard math. Stephen Hawking showed that black holes have entropy, a measure of hidden information, and their surfaces behave like holograms, storing data in ways we're still deciphering. Some theories take it further, suggesting that the first black holes didn't form from collapsing stars, but from pure information density, regions where reality's code grew so tangled that it folded inward, creating gravitational firewalls to quarantine the overload. The implications are staggering. If black holes are cosmic Turing machines, their evaporation via Hawking radiation might not be energy leaking away, it could be processed data, slowly radiating back into the universe in scrambled form. Ancient black holes could be relics of the cosmos's first computational crisis, their mergers less like crashes and more like servers syncing up. Even the mysterious uniformity of the universe, why distant regions look so similar, might trace back to these primordial processors smoothing out inconsistencies in the early code. Of course, skeptics argue this stretches the metaphor too far. Information isn't a physical force, and black holes don't have circuits. Yet cutting-edge work in quantum gravity keeps blurring the line between data and reality. Experiments with entangled particles and holographic simulations hint that spacetime itself might be built from information, meaning black holes could be less like objects and more like glitches in the cosmic operating system. Whether this theory holds or not, it flips the script on darkness. Black holes might not be the universe's trash cans. They could be its original programmers, silently running the code that keeps the stars from flickering out. And if we ever crack their encryption, we might not just solve astrophysics' biggest puzzles, we could uncover the source code of existence itself. Now, let's venture into the realm of cosmic shortcuts, wormholes, those hypothetical tunnels through space-time that could connect distant corners of the universe in an instant. But what if some of these wormholes never quite stabilized? Instead of becoming interstellar highways, they collapsed under their own weight, pinching off into black holes and leaving behind gravitational ghosts from the universe's earliest moments. Recent research into Einstein-Rosen bridges the theoretical foundations of wormholes suggests these structures are incredibly fragile. Picture a wormhole like a soap bubble stretched between 2 points in space-time. To stay open, it needs exotic matter or negative energy to prop it up, counteracting gravity's relentless pull. Without that support, the throat of the wormhole could snap shut violently, crushing itself into a singularity. The result, a black hole born not from a dying star but from a failed cosmic tunnel. The math behind this is as elegant as it is eerie. Studies in quantum gravity show that unstable wormholes don't just vanish, they leave scars. As the wormhole's throat collapses, the immense curvature of spacetime at its narrowest point could trigger a runaway gravitational collapse, sealing the exit forever. Some simulations even suggest these failed wormhole black holes might retain odd properties, unusual spins, or quantum echoes of their original structure, like cosmic fingerprints hinting at their origin. There's a tantalizing twist here. If wormholes flickered into existence in the early universe's frenzy, their collapses could explain some of the black holes we see today. Ancient mergers detected by gravitational wave observatories might not just be star-born black holes colliding. They could be the remnants of wormholes that never made it, their violent ends echoing across billions of years. Of course, proving this is a monumental challenge. Wormholes remain purely theoretical, and their fleeting existence would have left few traces. But as physicists refine models of quantum spacetime and gravitational wave detectors grow more sensitive, we might one day catch a signature, an odd spin, an unexpected mass that whispers of these cosmic shortcuts that failed. Until then, it's a thrilling reminder that black holes might not just be endpoints in space and time. They could be the wreckage of bridges that never quite held. From primordial black holes born in the Big Bang's afterglow to cosmic strings snapping like overstretched rubber bands, we've journeyed through 30 astonishing ways the universe's first black holes might have formed. Each theory isn't just a wild guess, it's a keyhole glimpse into the cosmos's deepest secrets. Whether it's the holographic universe encoding black holes as data glitches, or colliding multiverses leaving gravitational scars, these ideas stretch our understanding of reality itself. Some theories feel like science fiction consciousness birthing black holes through sheer chance, or entire universes hiding inside them. Others, like population, 3 stars collapsing into darkness or neutron stars merging in cosmic smash-ups, might be closer to the truth than we think. And let's not forget the radical possibilities, black holes as time crystals ticking through eternity, or relics of vacuum decay rewriting physics in their wake. So which theory speaks to you? Maybe it's the elegance of direct collapse black holes growing from pristine gas clouds untouched by metals. Or perhaps you're drawn to the quantum chaos of Planck-scale singularities flickering in and out of existence. Whatever resonates, one thing's clear. The universe's first black holes weren't just gravity's dead ends, they were cosmic innovators, shaping everything from galaxy formation to the fabric of spacetime. The beauty of science is that we're still discovering. Maybe the true answer lies among these 30 ideas, or maybe it's something even stranger waiting beyond the edge of our imagination. If these cosmic mysteries left you as awestruck as they did me, hit that subscribe button and let me know in the comments which black hole origin story feels most compelling to you. Until next time, keep looking up because the universe's darkest secrets often shine